Okay, you've just turned in homework number 1, right? And I haven't yet identified the grader for the course. I've asked a couple of people, but I'm waiting to hear back from one of them. So in general, my hope is that I'll be able to have your assignments graded within a week. But this first assignment may take a bit longer than that because I don't yet have a grader. So we'll do our best to keep up with things, and I want to get it back to you quickly so that you can learn from your mistakes and close the loop. I definitely understand the value of you getting immediate feedback on what you've submitted. I got a couple of questions about homework 1, but not as many as I was expecting, and I hope that means it's because you were able to figure things out pretty easily. I hope it's not the case that someone was struggling but too shy to ask for help. That would really make me feel bad. If you needed help but you felt embarrassed to come ask for it, that's not good. So call me on Teams, send me an email, you can call me on the phone, stop by my office. Anything I can do to give you help, I really am eager to do that, so please let me know. Your next assignment is due a week from today. That's available now on Blackboard. And today what we're going to talk about is vapor pressure and hydrostatics. So hydrostatics is where we're starting on chapter 3 in the book. Vapor pressure is the last topic from chapter 2. Any questions before we move on? All right. So what we're looking at here is a kettle of water that's boiling. And let's just think about boiling water for a minute. It seems straightforward. I mean, you've watched water boil when you're making spaghetti or making tea, and maybe you don't think much about it. What temperature does water boil at? In Celsius? 100, right. And what a strange coincidence, right? That it would boil at exactly 100. It's not a coincidence, obviously. That's kind of how they defined the Celsius scale is 100 is boiling, 0 is freezing. But water doesn't always boil at 100. It boils at 100 at sea level, but at other elevations, water will boil at a different temperature. And so, for instance, at the top of Mount Everest, where I don't know if anybody's boiling water up there, but they boil water maybe a little bit lower, making tea for the climbers. But on Mount Everest, water would boil at 69 degrees Celsius. So any thoughts or any speculation on why that would be? Is it because it's a different molecule up at Mount Everest? Does it go through some sort of a transubstantiation where it goes from H2O to something different on the climb up to Mount Everest? No, I see some shaking heads. It's obviously not that. It's still H2O. So why would it boil at a lower temperature at the top of that mountain? Yeah?
Less pressure, so it's easier to exist as a gas than a liquid.
Okay, less pressure. So you're rightly making the connection that at the top of the mountain, we all know that when people go up to Mount Everest, normally they'll use supplementary oxygen because the air pressure is lower. Down low, we have high atmospheric pressure. Up high, there's lower atmospheric pressure. So it's more difficult to breathe. And what it essentially means is that the pressure of the atmosphere is acting downward on the surface of the liquid. And it's resisting the escape of water molecules from the liquid phase into the vapor phase. So this is liquid water, and liquids have something called a vapor pressure where they're pushing back. So depending on the temperature, the molecules are banging around into each other. They have kinetic energy. And the warmer the water is, the more kinetic energy there is in the water molecules. And so they're moving around faster. And a greater proportion of them will have enough kinetic energy to escape from this interface, from the liquid-gas interface as the temperature increases. So at sea level, a lot of the molecules have enough energy to escape this pressure that's acting against it at 100 degrees Celsius. But when you're up at a higher altitude, there's less pressure that's keeping the the liquid phase, like less atmospheric pressure resisting the vapor pressure, and so you don't need as much temperature because you don't need as much kinetic energy for it to escape. So it's just a matter of kinetic energy and what temperature is required to have enough kinetic energy to overcome atmospheric pressure. So there's this balance between atmospheric and vapor pressure. And we're going to talk about vapor pressure in some detail today. So any questions about the things I've just been talking in terms of boiling water? So let's define some terms. Vapor pressure of a liquid is the pressure at which that liquid will boil. And of course, it's dependent on temperature as well. And so the vapor pressure increases when the liquid's temperature goes up. The more heat we add to a liquid, that energy goes into the molecules, and they're moving around with kinetic energy. And so there's more vapor pressure, more of a pressure for the liquid to escape from the liquid phase to the vapor phase. So here is a table of data that shows vapor pressure of water as a function of temperature. And if you remember back to chemistry, you probably remember that 760 millimeters of mercury. This pressure column is in units of millimeters of mercury. So it's the vapor pressure of water, and at 100 degrees, the vapor pressure of water is equal to the pressure that would exist at a depth of 100 millimeters of mercury. So like maybe you've never known what is meant by millimeters of mercury. It's related to that idea in the last class I introduced of like if there's a graduated cylinder of some liquid, then if you go down a depth of 760 millimeters, there's a certain pressure that exists at that depth. And so what we're saying is water at 100 degrees Celsius is pushing to get out of the liquid. Like there's a pressure where the molecules are trying to find their way into the atmosphere, and they're pushing back against the force of the atmosphere with a pressure that's equal to the same pressure that would exist at a depth of 760 millimeters if the liquid you were going down through is mercury. So this is a lot, I know. Are there any questions so far?
Seems so complicated for no reason.
Well, the universe is a complicated place. But it won't seem so complicated. It seems complicated now just because you're learning it all at the same time. Yeah. One interesting thing, I think, is that water has a vapor pressure even below zero. So think about what that means. That means that ice has a propensity to go from the solid phase into the gas phase. So maybe you remember back to those chemistry days a process known as sublimation. And sublimation is the direct transfer of a solid to a gas. And so when you see dry ice that looks like it's smoking, I mean it's not smoking, it's just that it's going from solid to vapor. Well, water does the same thing. So it's possible in like northern Minnesota in the dead of winter, you can wash your clothes, put them on the line, and they'll freeze, but then eventually the water will all be out of the clothes through the process of sublimation because it's very slow, but there is a little bit of pressure where the water's trying to get into the atmosphere even when it's as ice. So here's the same data as it's graphed. And what you'll notice is it's nonlinear. The more the temperature increases, the vapor pressure of water is increasing a lot. So one way to think about this is how quickly something will evaporate. It will evaporate very slowly at a low temperature. So if you have a pan of water at 40 degrees Celsius, you know, that water's not going to boil off, but it is going to evaporate away at 40 degrees Celsius. But it'll evaporate a lot faster at 80 or 90 because the vapor pressure is so much higher. So it's not a linear relationship. It's exponentially increasing. All right, so 100 is where the water is boiling, and that just means that the average molecule has enough kinetic energy to go into the vapor phase. And boiling doesn't mean that all of the molecules instantaneously go into the vapor phase. It's limited by how much additional energy is being added, because there's also this an amount of energy that's required for it to go through the phase change. Now the interesting thing is that we can get water to boil at lower temperatures if we take away some of the pressure. You know, at sea level, it's 1 atmosphere that's acting against the water. So 1 atmosphere at sea level is acting against the water, which means you have to bring the water up to 100 to get it to boil. But if we had a device where we pump out the gases, we pump out the air and we reduce the atmospheric pressure, we can get the water to boil at lower temperatures. And so let's take a look at a YouTube video that illustrates that point in kind of a fun way. First, we got to watch a COVID-19 commercial. Boy, I've been seeing a lot of those lately. At temperatures other than 100 degrees. Okay, so here's that same data that shows the vapor pressure. The other one we were looking at was millimeters of mercury. This one is units that we're more familiar with for the course, newtons per meter squared, or pascals. And so 101.3 kilopascals is the vapor pressure of water at 100 degrees Celsius. Just since we're on the subject of water going into the vapor phase, let's look at one other video that's kind of interesting that shows the immediate vaporization of really hot water so quickly lost all of its heat that it goes into the vapor phase almost immediately. All right. One of the interesting applications of liquids turning into a gas and going through that transition is a phenomenon known as cavitation. And here's kind of an interesting case study in cavitation that happened in Russia at the Sayano-Shushenkasa Dam. And this is the largest hydropower plant in Russia, and it's the 9th largest hydropower plant in the entire world. It's been around, I think, since the 1970s, and it's had a couple of little incidents over the years. But they had a really spectacular accident, spectacular in a bad way, in 2009. And let me tell you a little bit about it. Of course, the way that a dam like this works is that there's elevated water behind the reservoir, and that water flows through a pipe, and it has pressure because of the elevation difference between the water behind the dam and the elevation of the water downstream, in the receiving body. So water flows through these pipes, and it spins a turbine with that, the energy of the flowing water that's losing elevation, spins a turbine, and then that turbine is what generates electricity. And ordinarily, it's a very safe and environmentally friendly way to generate electricity. But there's a risk. When water is flowing really fast, the pressure of the water decreases. And you're going to learn about that when we start discussing the Bernoulli equation in Chapter 4. More of the reason why the pressure goes down. But just what you should know for now is that when water is moving quickly through a confined space, that the pressure decreases. And the pressure can decrease so much that it falls below the vapor pressure of the fluid. And so if the pressure surrounding the fluid is less than the vapor pressure, it begins to boil. And by boil, remember, what we mean is not that it's hot. It simply means that some of the liquid water molecules are turning into gaseous water molecules. It's vaporizing. So what you don't want is you don't want the water to vaporize as it goes through this power plant. And the reason why you don't want it is that when the water vaporizes. Remember that gases take up more space than liquids. If you boil water, it takes up more of a volume, and then when that air bubble collapses, it sends a shock wave through the water. What we're looking at here, this is an impeller. This is the metal part that's inside of a pump that accelerates a pump to cause it to flow through a pipe. And if you turn it the other direction and you already have flowing water that's at a pressure, an impeller can be used to generate electricity. So it's similar to like what drives a boat, right? You know that you've got a motor connected to a propeller, and that's what pushes a boat forward. Inside of a power plant, rather than pumping the water, you're using flowing water to generate electricity. And so in a power plant, what this impeller would do is it would translate the moving water into mechanical motion that's going to spin the generator. And these little defects in the impeller, this is not rust. It's not rusting or corrosion that caused those little pits. It is shock waves that occurred when water vapor bubbles collapsed. There's just enough energy there to cause a little flake of the metal to be taken away from the rest of the impeller. And what happened in this dam in Russia is that they had really fast-moving water that was cavitating, and over decades there was enough of this pitting and erosion of the impeller that it became a little bit imbalanced, and it was vibrating because there was more metal loss on one of the impellers than on the other. So this spinning turbine is connected to a spinning impeller, and it was vibrating a little bit. And unfortunately, several of the bolts that were holding the generator in place were disconnected, and several more of the bolts had cracks and fatigue because they were decades old and they hadn't been testing to make sure that the bolts still had their strength that they ought to. And what happened was one day it just all spectacularly failed. One of the generators that was spinning started to vibrate, and it vibrated more, and it kind of just cascaded out of control, and basically the entire generator just blew out the side of the building. It took the roof of the building off, a bunch of water filled the area, and it took this dam offline for months and months, and it had a huge economic impact. And a lot of the electricity that was used at this dam was utilized in the aluminum industry in Russia, and that's one of the few things that Russia exports in great quantities is aluminum. And so this one incident actually caused the price of aluminum across the world to spike because of a reduction in supply in Russia. So it's just kind of an interesting case study, and there are others too, of where this fluid property, the fluid property of vapor pressure, had kind of an interesting real-world impact when it wasn't managed in the correct way. So we'll talk more about cavitation later in the semester, but it's just kind of an interesting sneak preview of how fluid properties can be so important. The takeaway message is that if the water pressure is less than the vapor pressure of the liquid, then cavitation will occur. And you had a low pressure in this dam because the water was flowing so quickly. Okay, so we're done with chapter 2 and we're moving into chapter 3 now. Chapter 3 is all about one thing. It's all about hydrostatics. And what that means is the change in pressure in fluids that are at rest. So here's the hydrostatic equation. And what it means is that the change in pressure with respect to elevation is that it decreases at a rate of gamma, where gamma is the unit weight of the fluid. So remember, what's the unit weight of water? Anybody have that constant memorized so far?
9,810 newtons per meter cubed.
Perfect. That's right. 9810 newtons per meter cubed. So that's the unit weight of water. So what this is saying is pressure changes at that rate. And the minus sign just implies that, let's just take as an example, we've got a tank of water. This image on the left, it's a tank of water. We're measuring elevation starting at the bottom of the tank. If you go up through the fluid, the pressure is decreasing. That's why the minus sign is there, is that the pressure increases as you go down through the fluid, and pressure decreases as you go up through the fluid. Now, I'm sure you already knew that, right? Swimming in a pool, if you go down in the water, the pressure increases and you can feel it in your ears. And the opposite is that if you go upwards through the fluid, the pressure is alleviated, pressure is reduced. So this minus sign is just indicating that you have an opposite direction between increased elevation and increased pressure. So let's think about the units here. Are the units consistent on the left-hand side of the equation as they are on the right-hand side of the equation? So what we've just said is that the unit weight of water has units of newtons per meter cubed. Okay, so on the left-hand side of the equation, newtons per meter cubed. Now what about the left-hand side of the equation? So change in pressure, pressure is newtons per meter squared, and then we're dividing it by change in elevation, which is meters. So yeah, those units are consistent on the left side and the right-hand side of the equation. So for water, if you go down 1 meter into water, the pressure will increase 9810 newtons per meter squared if you go down 1 meter. Now, let's talk about fluids that have a uniform density, meaning that the density of the fluid doesn't change as you go up or down through it. So liquids, this applies for liquids. Assuming that you have a uniform density and specific weight, then integrating that hydrostatic equation will yield this expression for piezometric pressure. Highlight or put a little star or somehow make a note to yourself this equation for piezometric pressure. We're going to use it several times through the semester, although we won't do any calculations with it today. It's just a way of keeping track of both the pressure and the elevation that you're at in a fluid. So remember this illustration of a tank of water. So if we wanted to keep track of both the pressure and the elevation at a certain point, we would use piezometric pressure for that. So P sub Z, the piezometric pressure, accounts for not only what's the pressure at a location, but also how high above the datum are you at that point. Another way that we can express this is with piezometric head. And so if you divide each term by gamma, then as you're moving through a fluid between 2 points, the piezometric head is constant. So what that means is if you go down in elevation, you'll be losing Z, but increasing pressure. And so between 2 points in a static fluid that's not moving, the piezometric pressure and the piezometric head is the same. So P sub Z1 equals P sub Z2, and also P1 divided by gamma plus Z1 is equal to P2 divided by gamma plus Z2. Just as you go down through the fluid, the pressure goes up. So you're losing elevation, but you're gaining pressure. And there's just this, this exchange between elevation and pressure that occurs in a static fluid. So that's the hydrostatic equation. I've just written it out on the board, and we see it on the screen here. We can use this formula to find out what is the pressure at a certain depth. And here's an example where we're going to do just that. Okay, so here's the hydrostatic equation. And what we know here at location 1 is at an elevation of 34 meters. Now we don't know exactly where the datum is. Does that mean above the bottom of the tank? Does it mean above sea level? Ultimately, it doesn't matter. as long as location 2 has the same datum. And so let's assume that it does. Location 1 and location 2 are measured according to the same elevation datum. And what I'd like you to do is use the hydrostatic equation here and find the gauge pressure at location 2. So we know P1, we know gamma because it's water, we know Z1, we know Z2, the only unknown will be P2. So find P2 in both gauge and absolute terms. And remember, the way that we can convert between gauge and absolute, P absolute is P gauge plus 101,325 Pascal. That's the conversion between absolute and gauge pressure. All right, so let me pause for a second, and you calculate P2. All right, so you can see on the whiteboard I've solved this one, and I've done it in quite a lot of steps. You know, you probably could solve the whole thing in your calculator without actually writing anything on the paper, but I think it's better if you just show yourself the evolution of ideas and try and keep track of all the algebraic moving around. That way, if you make a mistake, it's easier to pinpoint maybe where the error was, especially since other people are going to be reviewing your work through the years. So in any case, what we've got is rearranging this equation to solve for P2, and what we get is 144,480 pascals is the gauge pressure, and the absolute pressure, we add 101,325 pascals to that and get 245,805. So did anybody else get those same values? Good. All right. Any questions? You've just applied the main idea of Chapter 3. I mean, everything else is just applications of this. Some of them will get a little tricky, but at the core, it's just all that pressure increases as you go down through a fluid, and it increases at the rate of gamma. So the unit weight of water is the rate that pressure is increasing. Every time you go down 1 meter through water, the pressure is increased by 9810 pascals. Of course, different fluids have different unit weights. So here's the full hydrostatic equation, and we can abbreviate it if we're just interested in keeping track of changes in pressure through a fluid. And so the delta P would be the difference in pressure between 2 points. Delta H is the vertical deflection between location 1 and location 2. So it's the change in Z between 1 and 2. We're just saying delta H is the vertical component of how far apart they are. So delta H is not the inclined distance. Delta H is just the vertical distance between these 2 points. Okay? The lowest point of the ocean is in the Marianas Trench, and it's called Challenger Deep. That's the deepest part of the ocean. And it's more than 10,000 meters underwater. So 10,911 meters underwater. So what's the pressure change from the surface of the ocean to the bottom? Now let's neglect the fact that actually the seawater compresses itself a little bit at that depth. So the pressure, the true pressure may be a little bit greater than what we're going to calculate by assuming that the density is uniform. But the unit weight of seawater is greater than fresh water because it's got salt dissolved in it. The unit weight of seawater is 10,100 newtons per meter cubed. So apply that abbreviated hydrostatic equation and find what's the pressure at Challenger Deep. Delta P is delta H times gamma. So the delta H is 10,911 meters. The unit weight of seawater, 10,100 newtons per meter cubed. So 10,911, 10,100. Boy, there's so many numbers here, I don't know if I can write them all. 110,000, I think it's 110 megapascals, right? Let's see, 000. Yeah, 110 MPa, megapascals. That'd be enough to make your ears pop. And collapse your submarine and everything else. Okay, so that's the abbreviated hydrostatic equation. You'd use it just if you want to find the change in pressure. If you're going down through a fluid, of course the pressure increases. If you're moving upwards through the fluid, the pressure is reduced. Any questions so far about the hydrostatic equation? Oh, things get tricky when you layer fluids on top of each other. Pressure is additive. So consider the case of, what if you had oil with a specific gravity of 0.75? Remember, specific gravity is the ratio of density or unit weight to water. That's what we mean by specific gravity. So it's forming a layer of 1.1 meters on top of a tank that otherwise filled with 10 degrees Celsius water. So the total liquid level of the tank is 4 meters. All right, so what we want to do is we want to find out what's the pressure at the bottom of the tank. And our strategy for this one is we have to go in steps. We'll start at the surface where we know the pressure and gradually work our way down. So let me do this. All right. Even when it's a simple sketch, I think it's a good idea in your homework to draw the system. You know, like even if you've got the image of it right there in front of you on the handout, I think it's a good idea just to draw the system. Drawing it with your own hand helps you to understand what's going on. So we've got a tank that's got 4 meters of liquid in it. 4 meters of liquid, and the oil layer has a depth of 1.1 meters. Now it's not telling us directly. This is water, and we want to know what's the pressure at the bottom of the tank. And so first of all, we're going to have to find out how thick is that layer of water. Well, it's 4 minus 1.1. So 2.9 meters is the thickness of that water layer. And the strategy you should apply when you're solving the hydrostatic equation is start where you know something and work towards the unknown. So where we know something is here at the surface where it's in contact with air. And what we know is that the pressure there, the pressure of the air and the liquid is the same at the interface. So I'm going to call this location 1, I'm going to call this location 2, and then the bottom of the tank is location 3. Pressure at location 1 is 0 pascals. Air equals liquid pressure at the interface. It's just the air pressure, if you haven't gone down through the fluid at all, then the pressure of the oil right at the point where it's contacting the air is going to be the same as the air pressure. Okay, now the hydrostatic equation is that the change in pressure is the change in elevation multiplied by gamma. So at location 2, it's going to be the pressure at location 1 plus delta H times gamma. So plus some change, because we're going down through the fluid, the pressure is increasing. Okay, so the pressure at location 2 is the pressure at 1, which was 0 pascals, plus the delta H of 1.1 meter, that's the vertical distance between them, and the unit weight of the fluid for oil. Do we have the oil characteristics? It told us that the SG of the oil is 0.75. So if we want to know the gamma of oil, that means it's the SG of oil multiplied by the gamma of the water. Very good. That's right. Okay, so 0.75 times 9810 newtons per meter cubed. And if you've got your calculator, you can follow along. Keep me honest. I think the unit weight of the oil is going to be 7357.5 newtons per meter cubed. Okay, so that's what we use, is we're going down through oil, so we need to use the unit weight of the fluid that's between the 2 points. 7357.5 newtons per meter cubed. Okay, so that quantity is 8093.25 newtons per meter squared. So that's the pressure at location 2. P2 is 8093.25 newtons per meter squared. So what do you think we're going to do to find P3? What's been the pattern so far?
Head to pressure above.
That's right. You start with the pressure at 2, and then you're going down through the fluid, and the pressure is increasing. What do we use for the gamma between 2 and 3? 9810. We use the gamma of water. You know, there's oil above it, but between 2 and 3, we're not going through oil, we're going through water. So that's why we'll use the unit weight of water. So P3 is P2 plus delta H times gamma. So it's 8093 newtons per meter squared plus the delta H of 2.9 meters and the unit weight of 9810 newtons per meter cubed. Wait for a moment for the screen to warm up. Okay, so we found the pressure at 2 was 8093. The pressure at 3 is just however much there was at 2 plus the change, because we're going from 2 to 3. That's an increase in pressure. So that increase between the two interfaces is 28,449 newtons per meter squared. And the final answer here is that the pressure at 3, the bottom of the tank, is 36,542 pascals. So does everybody get the pattern? That you work from point to point, and you have to put one of these intermediate steps anytime there's a change between one liquid and the next. So you can't just go all the way from the top of the tank to the bottom of the tank in a single step if there's more than one different kind of liquid. So if there's 2 liquids, you're going to have to break it up into 2 steps. What about if there's 3 liquids? All right, I'm not going to talk on this one. I'm going to stop for a moment, and I'd like you to see if you can figure out this brain teaser. Of course, it's encouraged to collaborate with your classmates. You know, scoot up next to somebody, cough in their face, and ask them what they got on part of the problem. We're given some information here. We've got the hydrostatic equation. We know the specific gravity of this first liquid. We know the density of the second liquid. And we don't know the unit weight of the third. So, you know, the hydrostatic equation, you don't always just solve for delta P. What if you're given the delta P? Then you could solve for delta H, or maybe if you know delta P and delta H, you could solve for gamma. And that's what you're doing in this one. Just to change things up a little bit, the purple liquid here, I tell you the distance, I tell you the pressure at a certain point, and so I'd like you to go through the steps and determine the unit weight of that purple fluid based on all of the data that you're given. And the starting point, here's your hint. You should start where you know something and work towards the unknown. And what you know is that the pressure of air is 0 gauge. So this pressure, where I say 45 kilopascal, that's the gauge pressure. So that means start with a pressure of 0 up at the top. All right, so I'll pause. I'll circulate around if you want to check your work or see if you've got the right answer. I'll have the solution, and hopefully we can figure this thing out together. Okay, so we're going to go through this one step by step. We start where we know something and work towards the unknown. What we know at the beginning is that the pressure of the air is 0. And so that means that whatever this liquid is on the top has 0 pressure at the top of the layer. And the pressure is going to increase as we go down through the fluid. And it's going to increase more. And so let's take a look at the solution for this one and just see if we had some of the same ideas. We got 3 fluids, and we're going to use the pressure variation to classify the unit weight of the third fluid. I don't know why, but for whatever reason, I called this top layer 0, and I called this interface 1, 2, and 3. So if you called it like 1, 2, 3, and 4, that's fine. It's just I labeled my interfaces according to that methodology for this one. So the pressure of the air is 0, and then the pressure at the bottom of the first layer will be 0 plus some increase. And the increase is 0.5 meter is the thickness of the layer, and I use the specific gravity that's provided in order to calculate the unit weight. So 0.78 times 9810 is the unit weight of that top layer is 7651.8 newtons per meter cubed. So here's the pressure, 3,825.9 pascals at the bottom of the first layer. Now the pressure at the bottom of the second layer is going to be that first layer pressure plus some more. So it's going to be plus the delta P that accumulates as we work through the second layer. We're given the density of the second layer, but not the unit weight. So P2 is P1 plus delta P. So it's the 3825.9 that existed at the bottom of the first layer, and then we're adding however much pressure accumulates as we go downward through a 1.55 meter thick layer of the second fluid, which has a unit weight of 9,800.19 newtons per meter cubed. So we were given the density. You can calculate the unit weight by multiplying it by G. So the bottom of the second layer has a pressure of 19,016.2 newtons per meter squared. Now P3 is already given. That's given as 45 kilopascals. So in other words, 45,000 newtons per meter squared. So the general form of the hydrostatic equation is delta P is delta H times gamma. And you can see I've rearranged that to solve in terms of gamma. Gamma is delta P divided by delta H. So we're just kind of turning this general hydrostatic equation on end to solve for gamma. So it's, by definition, unit weight is how much did the pressure change per change in depth. So between these two layers, we know the pressure at 2 because we've gone through the calculations to find that P2 is 19,016 pascals. So we know P2, P3 was measured to be 45,000. So the delta pressure between those two layers is 25,983. And finally, we can calculate the unit weight by dividing it by the 0.8 meters of depth. So as I was circulating around, I saw that some of the rest of you had gotten 32,480 newtons per meter cubed. So I think you've got a homework problem that's similar in concept to this. Any questions about the example? Okay. Remember, the class meeting, including these solutions to the examples, it's posted on YouTube. So there's a link to my YouTube channel on Blackboard. And then once you get to my YouTube channel, the videos are listed chronologically, or you can search by class meeting number. And this is class 4. Well, before we go our separate ways, let's take a look at the announcements. Homework 2 is what's on your radar for the class. You've got a week to do that one. And I guess most people in here are also in the lab, so the lab report will be collected at the beginning of lab on Tuesday. Of course, Monday's a holiday, right? We don't meet on Monday, but we won't see each other anyways because it's a holiday. All right, well, that's it for today. I'll see you next week.